All right, everybody, what I want to do in this video is I want to show you some examples of evaluating surface integrals of vector fields, otherwise known as flux integrals. We saw in 3 other videos, and I'll link to those in the description at the bottom. We talked about surface integrals with examples, specifically how to use the surface integral to calculate the surface area of a surface. And then we did a few examples of general surface integrals. We did a couple that were in parametric form, a couple that were in rectangular form. We also talked about the interpretation of the flux integral, again, in other videos. I'll post them, as I said before. And we even have a video that discusses the normal vector to a surface. So I have a couple of reminders here from those videos, okay? So our integrals are going to have this form to them. F, of course, is our vector field. ds, we showed, was equal to the magnitude of the cross product of these two vectors, partial of r with respect to u, cross partial of r with respect to v, dA, where that cross product is actually the normal vector to the surface. Now, let me say this at the outset. I do assume understanding of parametric surfaces. Okay, so we don't have to go into that. And if we did, it would make the videos much, much longer than they have to be. So definitely want to review those things from your previous experiences. Okay. All right, so with that, let's get started. Here's our first one. Okay. We want to find the flux of the vector field xyz across the surface S that is the upper half of the sphere centered at the origin of radius A. All right, well, let's see. Here's our surface, right? Let's use blue for that. Okay. And our unit normal vector would look like this. Okay. So I'm going to use the parametric version of the surface. And I'm going to make a note. I guess I can fit that here. So R of U and V in parametric form. Now, this is the upper half of the surface. And that's going to be for U between 0 and pi over 2. And for V between 0 and 2 pi. Okay. Now, my normal vector N, put that right here, I think, is this cross product. I have to take these partial derivatives of R with respect to U and R with, oh, that's a regular V, with respect to V. And I'll have you verify we should get the following. Okay. Now calculate the magnitude of that. And again, I'll leave it to you to verify the details. The magnitude of this is the radius squared times the sine of U. Okay. All right. So those two taken together tell us then that our normal unit normal vector then, oops, is equal to the following. So sine U cosine V, sine U sine V, cosine U. Okay. Then what I'll do is I'm going to take that, all right, and then I'm going to dot that with my vector field, mindful that I have to put the field in parametric form. Okay, now remember everybody that the vector field is right here. It's a radial field, right? X, Y, and Z. So I need to replace the X, Y, and Z with their parametric counterparts, which I get right here from the parametric representation of the surface. All of that is X, Y, and Z. So I'm going to I'll deposit all three of those into X, Y, and Z respectively. And we'll dot that with our unit normal vector right above. Okay, how's that look? All right, now when I dot these together, multiply the corresponding components, add everything together, and after the dust settles, again, I'll leave it to you to fill in the details. It should just come down to A. And because that's a constant, I'm going to stop right there, and I'm going to say that the flux integral of this over the surface we just calculated F dotted with N is equal to the radius of the sphere, which I can move through the integral symbol. Okay, now remember what this is from the previous videos? Remember what this is? Yeah, exactly. That's the area of the surface S, which in our case is the upper half of a sphere. So that's going to give us A times 1/2 of 4 pi A squared, which simplifies to 2 pi A to the third. Okay? All right, let's see. Let's try another one. This time our vector field is a constant field. So find the flux of the vector field 253 across the surface S. That is the portion of the cone, that's the upper half of the cone. Inside the cylinder, x squared plus y squared is equal to 1. All right, let's see. Quick sketch of that. All right, well, here's our cone, right? And it looks like that's going to run into our surface, or our other surface, which is the cylinder, x squared plus y squared equals 1. So that's going to look like this. Circle of radius 1 in the xy plane. So again, they're actually going to intersect each other. This curve right here is where they're going to intersect each other. So if I force these two things equal to each other, we're going to wind up getting this. So it's actually capped by the horizontal plane z is equal to 1 when you think about it. Okay. All right, so find the flux of the vector field across the surface S that is that portion of the cone inside the cylinder. So we're just looking at this portion of it right down here, all this part right here. Okay. All right, let's see. Now, here's my parametric representation of our cone. Oh, I forgot to put this as 1. Here we go. Okay. And that's going to be for u between 0 and 2 pi, v between 0 and 1. Okay. Now, based on this, the normal vector n, oops, will be as follows. And again, verify this. Now, don't take my word for it. You actually find this cross product and verify my result. The magnitude of that vector, okay? And so our unit normal vector will equal the following. Now, here's the thing. We typically want our unit normal vectors to be pointing upward and away from the surface. If you notice, look at the third component, the z component of my unit normal vector. That's negative. That means that this vector is actually going to be pointing downwards, right? So it would be looking something like this. Okay, but we want our unit normal vectors to point upwards. And so therefore, we need to take the opposite of that to be our n. Okay, so I'm going to make a note to myself. Need to use this. And notice what happens, gang. When you take the opposite of this vector, yeah, what will happen is the third component will become positive. As long as the z component is positive, your vector, your unit normal vector is going to be pointing upwards, which is what we want. All right, so we'll keep that in mind. Next, I'm going to dot the vectors f and my unit normal, okay? Mindful that I'm using the opposite, okay? All right, how's that look? Yeah? All right, now when I dot those together, multiply the corresponding components and add them. Okay. Now we also need d capital S, the differential element of surface area. Okay, and this is going to equal the magnitude of n dA. Okay, well, of course, the magnitude of n we found earlier was equal to v root 2 times dA. All right, so when I multiply everything together then, right, that's the next step, f dot n multiplied by the ds. We'll get the following integral. Okay, how's that look? All right. Okay, now notice the square root of 2 in the denominators will cancel with the 1 right here. So we cancel those, so that's okay. So then we'll rewrite our integral. And this is just straightforward integration now, everybody. Straightforward integration. I'll leave the details to you to fill in. Should get a value of 3 pi at the end. Okay? All right, so far so good, hopefully. All right, they're a little tedious, huh? They're a little tedious. All right, let's try the next one. Here we want to find the flux of the vector field, y, x, 2z, across the surface S that is the entire sphere centered at the origin of radius 1. Okay? All right, so there's our sphere, the unit normal, pointing upwards and away from the surface. Our parametric representation for the sphere, radius 1. Spheres come up a lot in these kinds of problems. Okay. I'll leave it to you to verify that the unit normal vector okay, is this. Next, I want to find the dot product of f with n. Okay. All right, and now here's my vector field. Now I need to put that in parametric form. Okay, so remember, this is my x, y, and z. So I'm going to replace y then with sine u sine v. Okay, replace the x with sine u cosine v. All right, and then replace z with cosine u. I'm going to dot that with my unit normal vector right here. The components, I'm going to add them together, and it actually simplifies rather nicely down to this. Okay, I'll leave that for you to fill in the details. All right. Now the differential element of surface area, ds, we'll need that. Yeah. I'll leave that to you to verify. And so our integral becomes the following. Okay. Now, of course, you're going to want to distribute the sign through. Okay. And once again, it's going to be straightforward integration. I'll leave those, I'll leave those details to you. Straightforward integration now, everybody. Okay. After all the dust settles, you should come up with 8 pi over 3. Okay, 8 pi over 3. As I always say, though, fill in the details. Actually do the double integral here, all right, and verify that you will get 8 pi over 3. Okay? All right, let's see. What's the next one? All right, find the flux of the vector field xy0 across the surface S given by z equals x squared plus y squared below z equals 4 with upward pointing normal vectors. So, gang, remember from your earlier experiences now, this is not the equation of a cone. This is the equation of a paraboloid. Okay, it's going to open upwards. So, quick sketch of that. Okay, and it's capped. It says, right, it says below z equals 4. So think of that as being trapped below the plane z equals 4. Of course, when you plug the plane z equals 4 into your equation, you're going to get 4 equals x squared plus y squared. It's actually the equation of a circle. Okay, so let's see. The parametric representations are paraboloid. Okay, now make sure you verify that as well. As I said, now I'm assuming that you've got an understanding of parametric surfaces, the most important surfaces, the ones that seem to occur most frequently. Those are going to be your spheres, your cylinders, paraboloids, and cones. Okay. Now the normal to the surface, of course, is this. Okay, and I'll leave it to you to take the cross product of these two partial derivatives, verify that you're going to get 2v squared, sine u, 2v squared sine u, and negative v. Okay, again, be careful. Notice your z component is negative here, right? We said upward pointing normal vectors, so we're going to need our vectors to pointing in this direction. Okay, this would have our normal vectors pointing downwards because the z component is negative. So like we did it in a previous example, we're going to have to wind up taking the opposite of our unit normal vector. Okay, but let's just go complete the calculation and then we'll go ahead and do that. Okay, calculate the magnitude of this and you'll find v times the square root of 1 plus 4v squared. So our unit normal vector then, okay, again, we see that negative right there. Okay, so we know we're going to want to use, so I'm going to make a note to myself, we're going to want to use this. Okay, take the opposite of that. And that will make the third component positive, which means our unit normal vectors will be pointing in the upward directions. All right, the next thing, we're going to calculate f dotted with n. With the understanding that we're using the opposite. Okay, so think of that red n right there, that with that minus right over here. Okay. All right, I do have to put my vector field. Remember, my vector field right here is x, y, 0. I do have to put that in parametric form. Okay. Its parametric counterparts are right here. Okay. All right, here's what we'll get. Okay, and when I dot corresponding components and add them together and simplify, I get the following result. Okay. Now ds is equal to this. Okay, and notice I've got that right here. All right. Actually, gang, when you think of it, I'm going to wind up multiplying these two quantities under the integral symbol right now, but look what's going to happen. Those two square roots are actually going to cancel. All right, so our flux integral is actually going to wind up looking like this then. Okay. And then of course when we write that as our double integral, we're going to wind up having this. And as usual, straightforward integration. Okay. And once again, I will leave it to you to fill in the details. Final result is negative 16 pi. Okay. All right, one more, last one. Last one. All right. By Coulomb's law, a lot of you are studying physics and engineering, so you've probably seen this before in your physics textbooks. If a point charge of q coulombs is located at the origin, then the force exerted on a unit charge located somewhere in space, say at the point xyz, is given by the inverse square field shown here, where r is the position vector of the point in space. If S is any sphere centered at the origin of radius a, show that the flux of this vector field through the surface is equal to 4 pi times c times q. All right, so as we've seen several times before, talk about a sphere, radius a. Here's its parametric representation. Okay. The unit normal vector, I'll leave it to you to verify. Okay. And I want to dot my two vectors together. Now I've got to put my vector f in parametric form. Okay. So let's see. That's going to be xyz divided by the magnitude of xyz to the third power. All right, so again, that should look like this: x squared plus y squared plus z squared to the 3/2. And I want to dot that with n. But notice this, gang. We're talking about the equation of a sphere. So all of this right here, right? What's the equation of the sphere? I'll put it right here, right? X squared plus y squared plus z squared equals a squared, right? That's the equation of our surface. And so down here, I'll just simply replace that quantity with a squared. Note that it's raised to the 3/2 power. Okay, so I'll write like this. And then x, y, and z, I'll grab those right from here. All All right, and of course, I'm going to dot that with n, which is right here, and I did not leave myself enough room. Sorry about that, everybody. Okay. Notice also, everybody, I can factor out an a from here, here, and here, and cancel it with the a to the third. Okay. Now, when I dot these two vectors together, multiply the corresponding components and add together, believe it or not, that whole thing, I'll leave it to you to verify, will just simplify down to the constant 1. So the dot product of these two just is just this constant. So I'm going to stop there, and I'm going to go right to the integral itself. Okay, I'll move that constant through the integral symbol. Okay, and as we've seen before, that integral there represents the area of the surface itself, which in our case is a sphere. And so our end result is going to be CQ over a squared times the surface area of a sphere, which is 4 pi a squared. A squares will cancel to get the result that we wanted to show. Interesting thing about this guy, notice that the radius doesn't actually even show up in the answer. So for this particular Coulomb's law, it's independent of the size of the sphere. The radius doesn't have anything to do with it. Okay. So hopefully that was enough examples for you. We could go on. That would just make the video a heck of a lot longer. So, but hopefully that's enough to get you started on your work.